Introduction to Thomas Young. Thomas Young was a remarkable polymath who made significant contributions to various fields, including optics, medicine, Egyptology, and linguistics. Born in 1773 in Milverton, Somerset, England, Young's curiosity and intellect were evident from an early age, as he demonstrated a prodigious talent for learning and a deep fascination with the natural world. As a young man, Young pursued a diverse range of studies, from medicine and physics to the ancient languages of Egypt and Greece. His groundbreaking work in optics, particularly his wave theory of light, challenged the prevailing particle theory and laid the foundation for our modern understanding of the nature of light. Similarly, his contributions to the decipherment of the Rosetta Stone were instrumental in unlocking the secrets of ancient Egyptian hieroglyphics, a feat that has had a lasting impact on our knowledge of the past. Early life and education. Thomas Young was born on June 13, 1773, in Milverton, Somerset, England, to a family of Quakers. From a young age, Young exhibited a keen intellect and insatiable curiosity, qualities that would shape his remarkable life and career. Growing up, he was encouraged by his family to pursue a wide range of academic interests, and he quickly excelled in subjects such as mathematics, languages, and the natural sciences. After completing his early education, Young went on to attend Emmanuel College, Cambridge, where he studied a diverse array of subjects, including medicine, optics, and linguistics. During his time at university, he developed a deep fascination with the nature of light and the workings of the human eye, which would later become the focus of his seminal contributions to the field of optics. Despite facing financial challenges and some resistance from his Quaker community, Young remained dedicated to his studies and continued to push the boundaries of scientific understanding. Even as a young scholar, Young demonstrated a remarkable breadth of knowledge and a talent for tackling complex problems from multiple angles. His insatiable curiosity and interdisciplinary approach would ultimately lead him to make groundbreaking discoveries in a wide range of fields, from the nature of light to the decipherment of ancient Egyptian hieroglyphics. These early experiences laid the foundation for Young's remarkable career and his lasting impact on the scientific community. Contributions to optics. Thomas Young's contributions to the field of optics were groundbreaking and laid the foundation for many modern optical theories and applications. One of his most significant achievements was his wave theory of light, which challenged the prevailing corpuscular theory of the time and provided a more comprehensive explanation for various optical phenomena. Young's seminal experiments with double-slit interference demonstrated that light exhibits wave-like properties, such as interference and diffraction. These experiments, which involved shining light through two narrow slits and observing the resulting interference pattern, provided compelling evidence that light is a wave rather than a stream of particles. This insight had far-reaching implications, paving the way for the development of the modern wave theory of light and the understanding of the dual nature of light as both a particle and a wave. In addition to his groundbreaking work on the wave theory of light, Young made significant contributions to the understanding of color vision and the human eye. He proposed the trichromatic theory of color vision, which states that the human eye has three types of color-sensitive receptors that allow us to perceive a wide range of colors. This theory, which was later expanded upon by others, has become a fundamental principle in the study of color perception and the development of color imaging technologies. Wave theory of light. The emergence of the wave theory. In the early 19th century, Thomas Young challenged the prevailing particle theory of light proposed by Isaac Newton. Young's groundbreaking experiments with interference patterns demonstrated that light behaves as a wave, rather than a stream of particles. This wave theory of light revolutionized our understanding of the nature of electromagnetic radiation, paving the way for further advancements in the field of optics. Wave theory of light. Explaining diffraction and interference. Young's wave theory provided an elegant explanation for the phenomena of diffraction and interference, which were previously unexplainable by the particle theory. By modeling light as a wave, Young was able to show how light waves could interact constructively or destructively, resulting in the intricate interference patterns observed in his famous double-slit experiment. This breakthrough laid the foundation for a deeper understanding of the wave-like nature of light. Expanding the wave theory. Building upon Young's initial work, other scientists like Auguste and Jean Fresnel further developed the wave theory of light. Fresnel's mathematical formulations accurately predicted a wide range of optical phenomena, including the bending of light around obstacles and the behavior of polarized light. These advancements solidified the wave theory as the dominant model for understanding the propagation of light, laying the groundwork for modern optical physics. Interference experiments. Thomas Young's groundbreaking interference experiments in the early 19th century were instrumental in establishing the wave theory of light. By passing a beam of light through two narrow slits, Young was able to observe the resulting interference patterns, alternating bands of bright and dark regions on a screen. These interference patterns were a clear demonstration that light behaves as a wave, with the bright bands representing areas where the wave crests from the two slits constructively interfered, and the dark bands representing areas of destructive interference. Young's careful measurements of the spacing and position of these interference fringes allowed him to calculate the wavelength of the light being used. The wave-like nature of light was a revolutionary concept at the time, overturning the prevailing particle theory of light. Young's ingenious interference experiments provided the critical empirical evidence needed to prove the wave theory and transform our understanding of the fundamental nature of light. Young's modulus. One of the lesser-known yet significant contributions of Thomas Young was his work on the concept of Young's modulus, a fundamental measure of the stiffness of solid materials. Young's modulus, also known as the modulus of elasticity, is a crucial parameter in engineering and materials science, as it quantifies a material's ability to withstand deformation under stress.
Young's modulus. 1.2 times 10 to the power of 11 n/m superscript 2. The typical value of Young's modulus for steel, one of the stiffest and strongest common engineering materials. 70 GPa. The Young's modulus of glass, an important and widely used material in construction, optics, and various industries. 0.5 GPa. The relatively low Young's modulus of rubber, which explains its flexibility and ability to undergo large deformations without permanent damage.
Young's modulus. Young's seminal work in this field laid the foundation for the understanding of the relationship between stress and strain in solids, a relationship that is crucial for the design and analysis of structures, materials, and mechanical systems. His insights into the elastic behavior of materials have had far-reaching implications in fields ranging from civil engineering to biomechanics. Hieroglyphic discoveries. Deciphering ancient scripts. Thomas Young made significant contributions to the decipherment of ancient Egyptian hieroglyphics, a feat that had eluded scholars for centuries. By analyzing the Rosetta Stone, which contained the same text written in hieroglyphics, Demotic script, and ancient Greek, Young was able to identify the phonetic values of several hieroglyphic characters, laying the groundwork for the eventual complete decipherment of the script by Jean-François Champollion. Hieroglyphic discoveries. Unlocking the mysteries of the past. Young's work on hieroglyphics opened up a new window into the ancient Egyptian civilization, allowing scholars to gain unprecedented insights into their language, culture, and history. By decoding the complex symbolic system of hieroglyphics, Young helped bridge the gap between the modern world and the rich, enigmatic world of ancient Egypt, sparking a renewed interest and fascination with this ancient civilization. Collaborative efforts. While Young made significant strides in the decipherment of hieroglyphics, his work was not done in isolation. He collaborated with other scholars, exchanging ideas and building upon each other's findings. This collaborative approach was essential in unlocking the secrets of the ancient scripts, as it allowed for a more comprehensive and nuanced understanding of the language and its cultural context. Medical contributions. In addition to his groundbreaking work in optics and physics, Thomas Young also made significant contributions to the field of medicine. His research on human vision and the eye's physiology laid the foundations for our modern understanding of how we see and process visual information. Jung's studies of the human eye's lens, retina, and optic nerves helped advance the understanding of vision and visual processing. He proposed the trichromatic theory of color vision, suggesting that the eye contains 3 types of color-sensitive receptors, laying the groundwork for our modern understanding of color perception. Medical contributions. Beyond vision, Jung also made important contributions to the field of medicine more broadly. He conducted research on the mechanics of human joints and introduced the concept of Young's modulus, a measure of a material's stiffness that is still used in engineering and biomechanics today.
Legacy and impact. Optics. Pioneered the wave theory of light. Hieroglyphics. Made key contributions to deciphering Egyptian writing. Medicine. Advances in physiology and eye-related treatments. Thomas Young's prolific scientific career left an indelible mark on numerous fields, from optics to Egyptology. His groundbreaking work on the wave theory of light revolutionized our understanding of the nature of electromagnetic radiation, paving the way for later breakthroughs in physics. Beyond his optical achievements, Jung also made significant contributions to the decipherment of Egyptian hieroglyphics, helping to unlock the secrets of an ancient civilization.
Legacy and impact. In the realm of medicine, Jung's fascination with the human body led to important advances in physiology and ophthalmology. His research on the mechanics of the eye and the perception of color continue to inform our modern understanding of vision and visual processing. The versatility and depth of Jung's intellect are truly remarkable, as he seamlessly transitioned between disciplines, always driven by an insatiable curiosity and a desire to push the boundaries of human knowledge. Thomas Jung's lasting impact can be seen in the widespread adoption of his scientific principles and the enduring influence of his work on subsequent generations of researchers and scholars. His multifaceted legacy serves as a testament to the power of interdisciplinary thinking and the transformative potential of a curious and analytical mind. Conclusion. In conclusion, the life and work of Thomas Jung stand as a remarkable testament to the power of human curiosity and the transformative potential of interdisciplinary exploration. From his groundbreaking contributions to the wave theory of light and the field of optics, to his pioneering work in hieroglyphic decipherment and his medical advancements, Jung's legacy continues to inspire scientists, scholars, and thinkers across generations. The depth and breadth of Jung's intellectual pursuits are a testament to his insatiable thirst for knowledge and his ability to synthesize diverse disciplines into cohesive, enlightening frameworks. His tenacity in the face of skepticism and his unwavering commitment to the pursuit of truth have left an indelible mark on the scientific landscape, paving the way for future generations to build upon his foundational discoveries.